Hello everybody and welcome to another session with me today. Again, I'm working on drakon renderer. Now, what are we going to be doing today? Let's dive into the code and let me show you what I came up with. So during the last two sessions, I believe, I was really struggling a bit with the concept I wanted to achieve, and that was to capture all the paths leading us in the drakon diagram from selected divergence points to selected convergence points. And let me explain what I mean. We're still working on valent points, and this is in order to get those valent points injected into the diagram automatically. So what I call divergence points is an icon from which multiple different paths start, and a convergence point is an icon in which multiple paths meet, like for example this one. Path number one, path number two. So the challenge is to detect pairs of divergence icon like this, and a convergence icon like this, and all the paths between it. And if those paths contain different number of valent points, or they are of different lengths, as for example here, we need to insert valent points to make them balanced and of equal length, where the length is the number of valent points. So I've thought long and hard about how to represent those paths leading from selected divergence points to selected convergence points. And I knew what I was looking for. I just couldn't express how I want it represented. And I finally think I have an idea. So the paths so we started here with divergence points being represented something like this. This is the icon name and its dependence. Right, so we can probably see some familiar faces here. Icon 3, that has two dependents, icon 4 and icon 6. Icon 6 that has two dependents, icon 8 and icon 7, etc., etc. And now the trick is to, for all of those divergence points, find paths that lead us to corresponding convergence points. So I was struggling a bit to represent this in the code, but I finally, I think, have a good idea. And this is an example of set of paths. You know what, maybe let's present it side by side. So let's make this a bit larger. Okay, so this is icon 3, and icon 3 is our divergence icon, and this is icon 6, and icon 6 is our convergence icon. Okay, so let me just make this font a little bit smaller. Is it icon 6 or is it icon 4? Let's see. No, this is icon 6, this is icon 4. Okay, so icon 4. No, hold on a second. This is icon 6. Oh God, remove alternative, let's see. Sorry, I keep. Sorry, I'm pointing at the wrong thing, and I'm confusing myself. Okay, forget about this. this is what we're looking for. Okay, so if we go back to the valent point, actually, this is it. Okay, apologies. Please forget everything I said in the last 2 minutes or something. Let's open this image. So what we're looking for here is, this is our icon number 3, 1, 2, 3, which is our first divergence icon. And this is icon number 6, which is our convergence icon, right? So if we were to track all the paths between icon 3 and icon 6, we can see 2 paths. Icon 3, icon 4, and icon 6, that's path number 1. And the second path is icon number 3 and then icon number 6. So I'm looking to capture paths like that, and I think I managed to do it. So you can see it's a list of lists where each list here is a chain of icons that lead us from a divergence point to our convergence point, aka divergence icon to convergence icon. So here we have a path leading us. The paths are kind of backwards, but you still get the idea. So we get 6 goes first, which is this, and then you immediately go to 3. Well, in this row, we get 6, 4, 3. Okay, so we want to achieve the same result for all our convergence and divergence points. And I think I have a function that does it pretty well. And I called it DC paths. So DC paths is what, this is just my naming. I'm not sure a term like that exists. So DC paths are paths connecting a divergence icon to a convergence icon. So if I run this now, and I run it for the first divergence icon, which is icon number 3, I should get paths that are not very pretty printed, but look something like this. Row number 1 has icon 6. It should also have icon 3. Sorry, icon 4, and then icon 3. And in row number 2, we should get icon 6 and then icon 3. Yep, and this is our first set of paths for this thing. Now, if we wanted to run it for another set of paths, actually, let's make it an experiment for now. We want to run DC paths for every divergence icon, and divergence icons we have here. It is icon number 3, icon number 6, icon number 7, which is, I believe, this guy, remove alternative, yes, and also icon 14, which I believe is check transit. Am I correct? Check transit. Okay, so if this doesn't work, let's not worry, but I think we're on the right track. And now, having those paths represented like this, it should be relatively easy to determine that within this list of lists, if your rows are of different lengths, it means that we need to rebalance them, aka add valent points to rows that contain lower number of icons than the max number of icons within a list of lists. And once we do that, then we can start thinking, okay, let's not insert icons to the graph at all now. let's populate the graph only with valent icons, and wherever it is suitable, let's place icons on top of valent points or inside of valent points, depending on how we decide to represent the relationship between icons and valent points. It sounds like a lot of work for something that should be as easy. If you only had pen and paper, it would be very trivial to just chart this. But unfortunately, this it's not. But it's fine. It's fine. Today I have much more energy for this. I think I'm finally on the right track with rebalancing those graphs or those paths. So let's do this. So I initially thought that we could pass a collection of just divergence icons like this, but it doesn't produce a good result. So what we can do is we can call this DC paths from a fold. Today is going to be probably a very short session. I don't have a lot of time, but still I wanted to make this video just to show progress. I'm pretty excited about this. So our accumulator is going to start empty, and this is going to be single convergence icon, singular, and here we just call this should be divergence icons. Let's move this to full screen. I'm not sure if the font size of the is correct. Editor, let's see. I think I had a zoom here somewhere. There we go. 3. And that is looking much better. And oh yeah, this is looking much better. So where were we? Yeah, the fold. So we call this fold. This structure looks weird, but it's that list of lists of paths. And what we can't forget is that list of lists of paths start with just one icon. So we represent it like this. This is all icons. This is convergence icons. And let's see if this works fine. Oh, of course. It builds, but it's not correct. So DC paths, we should have And I'm not sure this is going to be the data structure that we want ultimately, but for now, I just want to use it to illustrate the concept. So let's copy all these paths. Okay, so let's start with the end. So the end, before we see it, before we spoil it for ourselves, the end is a convergence point, a point where three different paths meet. Transport Finland, Transport Czech, and Transport Moscow. Let's see if we... how many paths we get here, but that depends on the divergence point. If the divergence point is this thing, which is I believe 14, we should only have two paths that are already balanced. Perfect. So this is 14, 15, 100. And in row 2, we have 100. I'm guessing this will be 16 and 14. 16, yeah, and 14. And they are balanced. Perfect. So we don't have to insert any valent points there. This will probably be quite confusing for people who are watching future sessions where valent points will be everywhere on every step in the diagram. But for now, I'm treating valent points just like as gimmicks, as like quote unquote icons that we insert to rebalance those DC paths, divergence point to convergence point paths. Now 8 is a convergence point. Where was it? Remove the brain. Here, this is convergence point 8, so we expect two paths that are not going to be equal. One is going to be of length 2, 6, 8, and another one is going to be of length 3, 6, 7, 8. Let's see. So this is probably going to be the 6, 7, 8. Or 6, 7, let's see. That's another end. Let's see. Okay, what do we have here? This is interesting. 100, 15, 14, 13, 7. So 100, 15, this is transport check. Oh, so it's this path. Okay. So this already reveals a very interesting part of the algorithm. We cannot be checking paths or the lengths of the paths like this, just in one go, in one fold, because as we balance one set of paths, say here, that will impact the balance of these paths most likely. So I know now that we'll never use this fold. We'll be doing first set of paths, balance, second set of paths, balance, and so on and so on. Okay, this is good. So here we have 100, 15, 14, 13, 7. And on the other hand, we should have from here. 100, this is, I don't know, 11 or 12. $16. Oh, that is interesting, because we go from the end all the way to 7, which is remove alternative, and we shouldn't be going that far. The path that we're interested in is, or maybe we should. But on the other hand, if we go from here all the way to the bottom, we don't have to be going from here all the way to the bottom, right? Because we would have already rebalanced the subgraph going through here. Let's see what else we have. Well, that was just 1. Okay, so this is not correct. We shouldn't have paths of length 1. Do we have convergence icons on the list of divergence icons? Oh, we do. And this is messing everything up. Okay, that's a lesson learned. But you know what? For now, I'm happy to wrap this session up. And I'm very grateful that I'm finally at this point where I can chart those sort of connections. So yeah, thank you very much for your attention. And I hope to see you during the next one. It looks like something is wrong with my camera, or at least in the preview. So I wish you all a fantastic weekend ahead, and I'll see you during the next one. Bye.